Welcome to this screencast where I'm going to give an introduction to operating systems and virtual memory. Operating systems are really the software layer that sits between the actual hardware of the computer and the programs that the user use in the computer. An operating system does a number of different tasks and will have a number of different components that allow it to do the various jobs it has to do. Handling interrupts and input-output requests, we've covered those in an earlier class. Dealing with the file system of the computer, so that's actually managing all the different files that go to disk. Working with device drivers, so being able to communicate with different hardware that might be plugged into the computer. Networking and security, but also something called memory management, which we'll see later in this class, and process management, and a division of programs into something called kernel space or kernel mode and user space or user mode. Some of the popular operating systems include Windows, as used throughout the university and the majority of computers, and as used, I think, by most of the students in the class. There's a variety of different Unix-based operating systems. These actually include the Mac OS X, Linux, the iOS, the iPhone operating system, Android, and many other operating systems are all based on something called Unix that runs at the sort of core. Before Windows, a lot of PCs ran something called DOS, Disk Operating System, and this was a sort of pre-Windows operating system for PCs. There are a wide range of other operating systems, Symbian, WebOS, BlackBerry operating system, and so on. When I asked the class at Paisley, what operating system do you primarily or solely use in your main computer, the range of replies I got were kind of what I expected. The majority of responses were Windows, with a few responses indicating Mac OS X, one response for Linux, and no other operating systems. This here is PC DOS. This is an example really of an early text-based operating system. So PC DOS was the IBM version of MS-DOS, the same disk operating system that Microsoft sold, but with the IBM name on it. Other companies sold compatible disk operating systems for PCs, but it was Microsoft's licensing agreement with IBM that allowed Microsoft to become the dominant software company for operating systems, and they were very successful in exploiting this in going into other areas of computing with Windows and with Office and so on. Ubuntu is a Linux distribution. Linux is an open source operating system, and the license allows companies or individuals to create their own distributions or versions of it. And Linux can work with or without a graphical user interface. So the graphical user interface we see here is not really a core part of the operating system itself. It's not really part of Linux. It's a Linux windowing system, and it's a Linux distribution that run on Linux. So the X Windows system, sometimes known as X11, provides an API for the graphical user interface. And there are different front ends for the user interface, KDE or GNOME. And so there's a lot of different software components here that we might think of as being part of the operating system, but are really different packages and with different authors and perhaps different companies behind them. But somewhere under this there is a core operating system called Linux. And Linux is a member of what we call the Unix family. And the Unix family has quite a long and convoluted history. Originally, it grew from a multi-user operating system development by Bell Labs, MIT, and General Electronics called Multics. There were problems with the development. Bell Labs decided to try again on their own, and a team there, including Ken Thompson, Dennis Ritchie, and Brian Kernighan, developed Unix. As a side effect of this, as a language to help them write Unix itself, Dennis Ritchie and Brian Kernighan created the C programming language to help them write the new operating system, and C obviously begat C++, and the whole C and C-like family of languages that are out there now all come from that development. And you'll see there are a variety of different versions of Unix that have come about from different origins. And many of the major IT vendors have their own version of Unix. So IBM have AIX, HP have their own version of Unix. You can kind of see that the Mac OS X is developed actually from the Next version of Unix. Next was a company that Steve Jobs was at after he first left Apple and before he rejoined Apple. He was with a company called Next. And then Sun, which is now owned by Oracle, developed their own version of Unix. There's a BSD, Berkeley Software Distribution, has also formed a number of different open source versions of Unix as well, called FreeBSD, NetBSD, or OpenBSD. And we can also see in the early 90s, the GNU Linux appears in this time scale as well, with the GNU project by Richard Stallman appearing a little bit earlier than that. So what are GNU and Linux? And GNU, G-A-N-U, for GNU is not Unix, indicated on the left with the Tux the Penguin mascot on the right for Linux. GNU was a project started in 1983 by Richard Stallman. This had the goal of creating a complete and free open source version of Unix. What they started working on first were many of the different tools and software programs that are part of a standard Unix distribution, editing tools, compiler tools, editors and so on. But the progress in developing the kernel of the operating system, the core of the operating system, was slow. In 1991, Linus Torvalds wrote his own core, his own kernel for a version of Linux, which he called Linux. And he certainly would have used many of the GNU tools, and he ported over the GNU software so it would all run on his operating system core. Because of this combination of tools, we basically had a more complete operating system. So there's the core itself and a whole range of tools around it required to really give it the features that users require and developers require. So Richard Stallman prefers to call the new system GNU/Linux, GNU Linux, whereas most people tend to just call it Linux. But it does use a lot of tools created from other people and from other sources. So the core or the kernel itself is the Linux part, and a whole range of software tools that it uses and relies on have come out of the GNU project or come out of other projects. So what is this kernel? What is the whole point of the kernel? And the kernel collects together the most basic set of operating system functions and features. There are some very key tasks that the kernel has to do. It has to manage the running of different processes. It has to be able to allocate memory to those processes, and it has to be able to process input and output. The kernel may also be in charge of managing the file system, running the device drivers, and carrying out a range of other tasks, but not necessarily. In fact, there are two key versions of kernel design. Monolithic kernel-based operating systems put the sort of file system, so the code that manages how files are saved to disk and how folders are organised and file naming works and so on, as well as device drivers for managing the different hardware that different installable hardware that you're using in your computer. So for example, if you change your graphics card, you need a different device driver for it. If you change your network card, it may need a different piece of software to talk to that network card that's different from how you would communicate with a different model or make of network card. So that's the device drivers. And so in the monolithic kernel operating system, the file system and the device drivers and virtual memory and the process management are all being run there in kernel mode. We see this here on the left. User applications, such as games or office applications, will be running here in user mode, in the user space. So there's a dividing line between the programs that we run on the operating system and the operating system itself, and another dividing line between the operating system and the underlying hardware. A microkernel based operating system tries to move as much as possible of the features into this user mode space here. So for example, device drivers are no longer part of the kernel. So device drivers now run as if they were other programs being run by the user. And even the file system itself, a file server, is a part of the operating system, but it runs in the user mode. What this is doing really is separating out some of the programs so that they don't have direct access to the hardware APIs and to the communication of the operating system itself. So above this red line at the top in the user mode, to communicate with the operating system or with other applications, programs have to use the application program interface that the operating system provides, and it limits and controls how programs at this top section are able to communicate and what they're able to do to the operating system and how they're able to access things. Any programs that are actually running in kernel mode have actually got a lot more control and a lot more access to the underlying memory and to the core operating system. So if a program running in the kernel mode crashes, for example, it can do very bad things and can crash the whole computer. But a program running in the user mode that crashes should just crash that one program and shouldn't affect other programs, and certainly shouldn't cause the whole system to crash. And so a microkernel based operating system tries to improve reliability by making things like device drivers into things that run in the user mode, in the user space. So this can help save the system and protect the system from some causes of crashes, and to help make the system more secure. There may be a performance hit, so there may be a performance cost of this, because device drivers no longer have the direct access. They now have to use an API, so there will be some slight cost in terms of the absolute performance. IPC that we see here, this acronym IPC, refers to inter-process communication. So this is how one process can talk to another process. So how your program, for example, might talk to the file server to be able to save some files to disk. And this is really just summarising what I've been trying to explain there. That with kernel space, there is direct access to the memory used by the operating system itself, and this can create security issues and reliability issues if a program crashes, or if there is a malicious program that has direct access to the operating system memory. Whereas applications and operating system modules can exist in this kind of user space that limits the direct access to memory and limits the direct access to hardware and to other applications. So in our modern operating system, we typically will have several programs running at the one time. So it's very common now to have your web browser up and an Office program up so you can work on a document, maybe a calculator, maybe a number of other applications, a file explorer, for example, any number of applications open at one time. And this can be true even if there is only one processor and one processor core in our operating system. So there's only one processor in our computer. It's only actually able to do one thing at a time, but to us, the end user, it appears that our computer is doing several things at the same time. And this is done by switching between the different running programs and processes at high speed so that a little bit of each can be done, and they all appear to be running at the same time to our eye, but really what's happening is only one's being run at a time, but the computer, the operating system, is able to switch between them quite rapidly. It can also take advantage of situations in which if one process is waiting for user input, it knows it can just pause that process, ignore that process just now, and do something else, and wait for that user input to occur. And where processes need to interact, the operating system manages this inter-process communication. Having mentioned this process management, it's also worth mentioning multiprocessing and multitasking at this point. Multiprocessing is a situation where a computer has more than one processor or core to run multiple tasks or programs. Modern processors are increasingly using multiple cores. It means the processor can actually do more than one thing at a time. So Intel processors for Windows-based computers, for example, are often now quad-core, so they have 4 processor cores. You may still find yourself in a situation where you're running more than 4 processes, but with multiprocessing, multiple processors are used to run multiple tasks. Multitasking, similarly you might encounter the term multi-threading, is allowing us to use multiple tasks running on one or more processors, so where we have multiple tasks, multiple processes on one processor. And this is where we need to do this sort of rapid switching between tasks, so that a processor can perform a little bit of each task, giving us the impression that all tasks are running at the same time. And so here's an example from Windows Task Manager. And in this case, we can see that there are actually 92 processes running. Now, most of the processes aren't really doing very much at the time, so they're not really using much of the processor. What is running, we can see here, we have Firefox and Internet Explorer. And you can also actually see here, something quite interesting is that Internet Explorer, there appear to be lots of Internet Explorers running. Each tab in Internet Explorer runs as a separate process. This helps maintain independence between the different tabs and helps aid security because each tab is a separate process. You can see I have PowerPoint running and a few other programs. We can also see the varying amounts of memory have been allocated to each process. So my computer is actually able to manage running a lot of different processes at the one time, some of which are actually using quite a lot of memory and potentially quite a lot of different processing power. But to me, they all appear to be running pretty much at the same speed. You can also see in total, CPU usage is actually only using 11%, even though I've got all these programs open, and I've only allocated 70% of the actual physical memory available on the computer. Now, if I've got lots of different processes and only one can actually be run at a time, how does the operating system manage that? Well, it uses something called process management. You can get 3-state and 5-state process management. Here we're only really going to look at the 3-state process management. So one issue is that a process that's waiting for input or output, and this can include signals from other processes. It might involve waiting on data to come from disk, as well as potentially data to come from the keyboard. So it's not just keyboard or mouse input, it could be data coming from another part of the computer system. So waiting for input-output can't do anything until it's got that input, so that process is blocked, and it can be marked as blocked. There are 3 possible states. As well as blocked, we have running, the process that's currently being run, and ready. So if a process is not blocked, but is not currently running, then it's ready. It's waiting to have its turn. It's in a queue of processes waiting to have a chance to do their thing. And all processes go through these different keys transitions. When a process is ready, it will be in a big queue of different ready processes, and when a processor is able to run one of those ready processes will be dispatched and switched into running mode. When it becomes blocked for any reason, it will transition to the blocked state until the input is ready, at which point it will receive a wake-up call and it can transition back to the ready list. Now, with preemptive multitasking, the operating system will regularly pause or block the running process so that other processes that are in the ready state can have a turn. If you have cooperative multitasking, then the running task will keep running until it voluntarily suspends or blocks itself. Windows, and I think many of the operating systems around now, will do preemptive multitasking. This helps block against a situation, or prevent a situation where the running task, maybe it crashes or ends up in an infinite loop, and it never reaches a blocked situation, and you end up with lots of ready processes that never get a chance to run. So with preemptive multitasking, the operating system will occasionally block the current running task, where it will move to blocked state, and if there's nothing else blocking it, it can go back to the ready list, but in the meantime, some other program gets its chance to do some processing. We have already looked at input, output and interrupt, so I'll not really say a lot about it here, other than the operating system is responsible for taking inputs, passing these to user applications where necessary, and really handles I/O for the applications. So when you press some keys, when you're typing in Microsoft Word, for example, the operating system receives those key presses and passes those messages on to the application. Device drivers are programs written to work with specific hardware systems, and they provide a simpler, more abstract interface that the operating system and applications can use. So the actual specific details of how a particular graphics card works or how a particular network card works may require different messages be sent to that graphics card or network card. So device driver software presents a more common library of functions that the operating system and applications can use, but it is able to pass the correct low-level messages down to the appropriate hardware. And the principle here is that the operating system developers and application developers really shouldn't need to know all the specific low-level details of all the different hardware systems that might be used. And indeed, when writing an operating system or application, you can't really know about the future devices that haven't yet been created. And so by having this separate device driver as a module that can be updated or added to an operating system, you're able to separate out that. In the remaining part of this screencast, we're going to be considering virtual memory. Before we get to virtual memory, let's think a little bit about the physical memory that a computer may have. So the RAM, we can consider the RAM as being a large address space where the very first element of RAM will be at address 0000, address 0, and there may be some content, some value stored in that. For example, that might be one single byte of memory. And the next byte in memory will be at address 1, and that will have some value in it. And so on, we can arrange all of memory, consider all of memory as being in one address space where every single byte in memory has a unique number to identify that one byte. So here we've got the first 5 bytes of memory here, and then further on, somewhere in memory, there's other data stored, and again, in a sequential order, every single byte can be addressed uniquely if we know the address of that one byte, the address of that memory location. So the memory address space gives us a unique numerical address for every byte or set of bytes, and addresses start at 0. Now the amount of memory, physical memory, you can address depends on the computer design. So a 32-bit x86 CPU limits you to 4 gigabytes of physical memory. In fact, some of the design decisions on the x86 family and some of how Windows operates actually limits you to a bit less than that on a 32-bit Windows installation. Now, early home computers And early computers and early home computers didn't really do operating system memory management. Only one program could be run at a time. So whatever program was running, it had complete access to the computer's main memory because only one program could potentially be running at a time. Now, this was often used and sometimes abused by expert programmers to squeeze maximum performance possible from computers of the time. Parts of main memory were also given over to system input or output. So some addresses would, instead of referring to RAM, would actually refer to input and output locations into other parts of the computer hardware. So for example, some of the memory addresses might actually be for the screen buffer for storing the values that are actually displayed directly to screen. So you could actually use memory operations to actually output directly to the screen, for example. But as computers advanced and main memory got larger, a range of different issues started to emerge. Some of the early issues with the Intel family of processors were that an individual process or individual program had a very limited address space available to it. Indeed, it only had 64K, but programs quite quickly grew to beyond 64K, so how could this actually operate? And so they came up with varying tricks to try and get past this, using segment and offset addressing to increase the total available memory. So you would have one address that would indicate the segment and a second address value to indicate the offset. So you're able to go to a particular block of memory and then use an offset value to refer to a piece within that block. So you're using two numbers to refer to one memory address instead of using one number to refer to a memory address. Modern memory management is paged and tends to use pages of memory. So the processor will often be able to load a complete page of memory at a time rather than necessarily accessing individual bytes from main memory. It might load a page, and a page might be, for example, 1024 bytes. It may vary from system to system. Now, with limited physical memory, as windowing operating systems grew and multiprocessor operating systems grew, they could reach a situation where they would struggle to fit all of the running programs into memory at the same time. And so here we've got a situation where we have an operating system running a number of processes, and they use up a certain amount of memory that's actually greater in size than the amount of physical memory installed on the computer. With the virtual memory, allows the use of secondary storage, allows the use of the hard drive as an extra memory space, and it gives the appearance of more memory than actually exists. Now, on the disk, swap files or swap partitions are used to add virtual memory to the physical memory. Programs can have partial residence, so a program might be partly in physical memory and partly in the virtual memory, stored on the disk. And scatterloading means that different programs can exist on different pages scattered throughout the physical and virtual memory. They don't have to be loaded in order. And this scatterloading and partial residence is typically invisible to the applications themselves. So the applications and people who develop the applications don't need to be aware of this. This is something that can be managed by the operating system. We can see this here where we have different blocks of memory from the virtual memory are loaded up into different locations in the physical memory, and some are actually being stored on disk just now. And this is a process that the operating system manages, and the applications don't really need to know much about. To manage this, the operating system will manage a page table. So it has a virtual address space that knows how much virtual memory there is, and the physical address space, which is how much RAM there actually is in the system, and this might be a lot less than the virtual address space. Each application may have its own virtual address space, and essentially there's some amount of data in the program that may be stored in a number of different locations in the main memory or may be stored in the disk in RAM. And the page table maps the virtual addresses to physical addresses, so the operating system is able to keep track of what data is actually in what location. Pages can be swapped to the disk if they're used infrequently or if the physical memory is full. And not all pages of the virtual address space are actually in the physical memory in the above diagram. So, for example, an application might want to access some of its own data, and it will have a virtual memory address to access. The operating system will intercept the call to access that data, and it will check that virtual memory address on the page table. And if that's currently in memory, it will give back the data as if the application is directly accessing the correct physical address. If that data is not currently in memory, then we've got a page miss. Then the operating system needs to load that data into physical memory, perhaps replacing an existing page which then gets copied back out to the disk. And that's a swap. We've swapped some data in to physical memory and some data from physical memory back out to the disk. If we have a situation where there is not enough physical memory on a system and it's trying to run too many applications and the applications are trying to access large amounts of memory at the same time, we can end up with thrashing. And that's a sort of constant disk swapping, and so you can sometimes hear this in older computers or computers that are not very well spec'd. When they're trying to run big tasks or data intensive tasks, you can end up in a situation where you have this sort of thrashing, the disk keeps whirring and the whole system slows down as it keeps having to copy data from memory to disk, from disk to memory, and it just keeps repeating this. On a modern PC with, say, 4 GB or more of RAM, you shouldn't really encounter disk thrashing too often. So applications running in the user space have their own virtual memory address spaces, and when they attempt to read or write to memory, these virtual addresses are translated to the actual physical ones by the operating system and the hardware memory management unit. And any attempts to access disks or file system are similarly mediated by the operating system, and this is generally invisible to the applications. So some other operating system features. So networking, operating systems will typically include an element to support networking. That's part of the kernel on Windows. Security, reliability in the file systems. And file systems may vary in how users can name files. So early versions of Windows and DOS, for example, limited file names to, I think it was 8 characters in the file name and then a 3-character extension. Unix file systems tended not to use extensions and allowed a different range of symbols in the file names and have always allowed spaces in file names, which Windows did not always do. Plenty of further reading, including the book Modern Operating Systems by Andrew Tannenbaum, in which he describes and gives enough detail for you to create your own operating system. The usual credits for the image material. And that's all for this week.